In this video, we're going to look at general properties of rational functions with any degree in the numerator and denominator. So just kind of extending what we talked about with rational functions with no exponents in them. So domain and vertical asymptotes are the same. We're going to set that denominator equal to 0 and solve it. Again, if there's no solution, then there's no vertical asymptotes and your domain is all real numbers. If the solution also makes the numerator 0, then we want to exclude it from the domain, but it's not a vertical asymptote. It would just be a hole in the graph. The same rules apply for horizontal asymptotes. We're going to use the degree of the numerator and denominator. The exception here is that if our numerator degree is bigger, there is no horizontal asymptote, but there is what we call an end behavior asymptote that we're going to have to look at. So in order to find that end behavior asymptote, we divide the numerator by the denominator and take the quotient only from that division, and that is my end behavior asymptote. To find the x-intercept, we're going to set the numerator equal to 0 and solve it, and to find the y-intercept, we're just going to plug 0 in for x. So let's just look at a couple of examples here. So this first one, we have x squared plus 2 over x squared plus 1. So first I'm going to work on the domain and the vertical asymptote. So I'm going to take the denominator, set it equal to 0, and I'm going to solve that. So this is going to give me x squared equals -1. When I solve that, I'm going to get an imaginary answer. So I do not need those when I'm talking about properties of a graph, because properties of a graph are only real numbers. So here we can just say no real solution. So that tells me two things. I have no vertical asymptotes, and my domain is all real numbers. Next, I want to think about horizontal asymptotes. So the degree of my numerator and denominator are both 2. I'm going to take my leading coefficients, which are both 1. So I have a horizontal asymptote at y equals 1. We're not gonna worry about range on these rational functions where we have exponents involved. We do, however, want to be able to talk about the intercepts. So remember, to find the x-intercept, we're going to set the numerator equal to 0 and solve. So I have x squared plus 2 equals 0. So solving this, we're going to get x squared equals -2. Again, that's going to give me no real solution. So that tells me no x-intercepts. And then finally, to find the y-intercept, we are going to evaluate f of 0. So we're going to plug 0 in for x. So we're going to get 0 squared plus 2 over 0 squared plus 1, which is going to give me 2. So my y-intercept is the point 0, 2. Taking a look at this graph, we can just use this to confirm the information that we came up with. So we can see that we have a domain of all real numbers here. We don't have any vertical asymptotes. We would have a horizontal asymptote at y equal 1, and then if we want to check our intercept, we can do second trace value at x equals 0, and we see that we have a y value of 2 there. All right, so taking a look at this example, we're going to set the denominator equal to 0 again, remember? So x squared minus x minus 6 equals 0. So if a quadratic here, you can solve with the quadratic formula. You can solve, I'm going to solve by factoring. This factors fairly easily into x minus 3 and x plus 2. So we get x equals 3 and -2. So this tells me that I have two vertical asymptotes at x equals 3 and x equal -2. I need to remove both of those numbers from my domain. So we're going to say -infinity to -2, and then -2 to +3, and then +3 to infinity. In this case, the degree of my numerator is 1, the degree of my denominator is 2. So since the degree of my numerator is smaller, I know that I have a horizontal asymptote at y equals 0. I want to find my x-intercept. So I'm going to set the numerator equal to 0, so x minus 1 equals 0. So we get x equals 1. So I have an x-intercept is the point 1, 0. And then for my y-intercept, we're going to plug 0 in for x. So I'm going to evaluate f of 0. So we're going to get 0 minus 1 over 0 squared minus 0 minus 6, which is going to give us 1/6. So my y-intercept is the point 0, 1/6. Again, using the calculator to double check some things. Here I have the graph. I'm going to go second trace value at 3. Y is undefined. At -2, y is undefined. You can see from the graph that you would have a horizontal asymptote at y equals 0. And then just double check a couple intercepts here. So at x equal 1, y equals 0. And at x equals 0, y equals 1/6. All right, last example. Here we're going to take the denominator, x minus 1 equals 0, so x equals 1. So we have a vertical asymptote at x equal 1. And my domain is going to be all numbers except 1, so -infinity to 1 and 1 to infinity. The degree of my numerator is 3. The degree of my denominator is 1, so my numerator has a higher degree. So this is where we have that end behavior asymptote happening. So this is where we have to divide to find that end behavior asymptote. We can do either polynomial long division or synthetic division. I'm going to use synthetic division. So I'm going to divide by 1, and then my coefficients are going to be 1, -3, 3, and 1. Remember, the 2 is my remainder here, and we actually ignore the remainder. So what I'm left with is y equals x squared minus 2x plus 1. So remember, this is my remainder, this is a constant, this would get an x, and this would get an x squared. So this is my end behavior asymptote. And then looking at my intercepts, in order to find my x-intercepts, we have to solve x cubed minus 3x squared plus 3x plus 1 equals 0. So I have a cubic function there set equal to 0. So in order to solve that, we're just going to graph. So from that graph, we can see there's 1, 0. So my x-intercept seems to be about -0.26, so -0.26, 0. And then to find my y-intercept, we're going to plug 0 in for x. So we're going to get 0 cubed minus 3 times 0 squared plus 3 times 0 plus 1 over 0 minus 1, which is going to give us -1. So my y-intercept is the point 0, -1. So taking a look on your calculator at this graph, again, we can confirm a couple things here. So we're going to go second trace value at x equals 1, y is undefined. I want to find my x-intercept, so we can do 0 here. And we get our -0.26, and then again, if we want to trick our y-intercept, we're going to do what's the value at 0, and we got the -1. So with our end behavior asymptote, we're going to go ahead and graph that end behavior asymptote in the y2. And then what I'm going to do is zoom out here. So what you can see from the graph is that the end behavior asymptote is showing us what the behavior of this function is just way out towards the left and to the right. It's not doing the same thing in the middle of the graph, but it's a simpler function that tells us what is happening at the left and right extremes of this graph.